On a cold January morning in 2006, beneath the skies of Cape Canaveral, humanity launched one of its most ambitious messengers into the cosmos. The New Horizons spacecraft, no larger than a grand piano, sat perched atop an Atlas V rocket, ready to embark on a journey that would take it farther than any spacecraft had ventured in such a short time. The air was crisp, filled with the salt of the nearby Atlantic Ocean, and the anticipation of thousands of scientists, engineers, and space enthusiasts who had gathered to witness this historic moment. The countdown echoed across the launch complex, each number bringing the dream closer to reality. When the engines ignited, flames erupted in brilliant oranges and whites, pushing against the Earth with a force of over 2 million pounds. The rocket lifted slowly at first, as if reluctant to leave our world, then accelerated rapidly, carrying New Horizons away from the only planet it would ever touch. Within minutes, it had pierced through the atmosphere, leaving behind the blue skies and entering the eternal darkness of space. This was not just another space mission. New Horizons carried with it the hopes of generations who had gazed at Pluto through telescopes, wondering about the mysterious world at the edge of our solar system. Discovered in 1930 by Clyde Tombaugh at Lowell Observatory in Arizona, Pluto had remained an enigma for 75 years. Even a mighty Hubble Space Telescope could only reveal it as a fuzzy, pixelated orb, its surface features hidden by the vast distance of nearly 3 billion miles. The spacecraft itself was a marvel of engineering efficiency. Weighing just over 1,000 pounds, it was designed to operate on less power than a pair of household light bulbs. Its heart was a radioisotope thermoelectric generator, powered by the natural decay of plutonium-238, providing a steady stream of electricity for its instruments and heaters. Without this warmth, the electronics would freeze solid in the extreme cold of deep space, where temperatures plunge to nearly minus 400 degrees Fahrenheit. New Horizons carried 7 scientific instruments, each carefully chosen to unveil Pluto's secrets. There was Ralph, a visible and infrared imager and spectrometer, named affectionately after the character from the Honeymooners television show. Alice, an ultraviolet imaging spectrometer, would study Pluto's atmosphere. REX, the radio experiment, would measure atmospheric composition and temperature by observing how radio waves bent as they passed behind the dwarf planet. These instruments, along with cameras, plasma detectors, and dust counters, represented the collective ingenuity of hundreds of scientists and engineers. But the journey would not be quick. To reach Pluto, New Horizons would need to travel for 9.5 years, covering a distance so vast that light itself takes over 5 hours to make the trip. The mission planners had plotted a course that would take advantage of Jupiter's immense gravity, using the giant planet as a cosmic slingshot to add speed to the spacecraft velocity. Without this gravitational assist, the journey would have taken several additional years. As New Horizons sped away from Earth at over 36,000 miles per hour, making it the fastest spacecraft ever launched at the time, it began a long period of hibernation. For much of the journey, the spacecraft would sleep, its systems powered down to conserve energy and reduce wear on its components. Only once every few months would ground controllers wake it briefly to check its health and perform maintenance on its systems. The people who built and launched New Horizons knew they were creating something special. Some had worked on the mission for decades, beginning with early proposals in the 1990s. The journey to get approval and funding had been nearly as long as the flight itself would be. But now, finally, their dream was in motion, sailing through the darkness toward a world that had captured humanity's imagination since its discovery. In the silence of space, New Horizons traveled alone, passing through regions where no human-made object had gone before at such speed. It carried with it a small canister containing some of Clyde Tombaugh's ashes, bringing the discoverer of Pluto along for the journey to the world he had first seen as a faint point of light among thousands in photographic plates. And so the voyage began, a testament to human curiosity and our desire to explore the unknown, to push beyond the familiar warmth of the inner solar system and venture into the cold, dark reaches where ice worlds orbit in eternal twilight. The journey of new horizons had commenced, and the universe waited patiently to reveal its secrets. 13 months after leaving Earth, New Horizons approached the king of planets. Jupiter, the massive gas giant that could swallow more than 1,000 Earths, loomed ahead like a great striped beacon in the darkness. This encounter was not merely a sightseeing opportunity, but a crucial milestone in the mission's trajectory. Jupiter's immense gravitational field would act as a cosmic catapult, adding 9,000 miles per hour to New Horizons' velocity and bending its path precisely toward distant Pluto. As the spacecraft drew closer through February 2007, its instruments awakened from their slumber, and cameras began capturing images of the giant planet and its diverse family of moons. Jupiter appeared in the spacecraft's view first as a bright star, then as a disk, and finally as a magnificent sphere painted in bands of cream, brown, rust, and red. These colors arise from complex chemistry in Jupiter's atmosphere, where clouds of ammonia ice, ammonium hydrosulfide, and water interact with the planet's powerful magnetic field and solar radiation. The most prominent feature in Jupiter's turbulent atmosphere is the Great Red Spot, a storm larger than Earth that has raged for at least 4 centuries. New Horizons observed this enormous anticyclone in unprecedented detail, watching as winds exceeding 400 miles per hour churn the storm's edges. The spacecraft's infrared instruments penetrated deeper into Jupiter's atmosphere than visible light could, revealing temperature structures and cloud patterns at different altitudes. But Jupiter itself was only part of the show. The planet's 4 largest moons, discovered by Galileo Galilei in 1610, provided their own wonders. Io, the innermost Galilean moon, is the most volcanically active body in the solar system. New Horizons captured extraordinary images of volcanic plumes erupting from Io's surface, fountainin sulfur dioxide gas and particles hundreds of miles into space. The spacecraft witnessed the volcano Tvashtar, sending a plume soaring 200 miles high, illuminated by sunlight against Io's limb, creating one of the most stunning images of the entire Jupiter encounter. This volcanic activity is driven by tidal forces. As Io orbits Jupiter, it is constantly squeezed and stretched by the gravitational pull of Jupiter and the other large moons, particularly Europa and Ganymede. This tidal flexing generates tremendous heat within Io's interior, keeping its rocks molten and driving the continuous volcanism that has painted its surface in yellows, reds, oranges, and blacks from sulfur and sulfur dioxide compounds. Europa, the next moon outward, presents a completely different character. Its surface is a shell of water ice, smooth and young, crisscrossed with cracks and ridges that resemble pressure fractures in Arctic sea ice. New Horizons observations added to evidence that beneath Europa's frozen crust lies a vast ocean of liquid water, kept warm by tidal heating similar to what powers Io's volcanoes, though less extreme. This ocean may contain twice as much water as all of Earth's oceans combined, making Europa one of the most promising places to search for life beyond our planet. Ganymede, the largest moon in the entire solar system, exceeds even Mercury in size. Its ancient, cratered terrain tells of a violent past, while grooved regions suggest geological activity billions of years ago. Ganymede is the only moon known to generate its own magnetic field, creating a miniature magnetosphere within Jupiter's much larger one. New Horizons studied these magnetic interactions, gathering data about how Ganymede's field deflects Jupiter's intense radiation and charged particles. Callisto, the outermost Galilean moon, appears as the solar system's most heavily cratered object, its ancient surface preserving impact from the early solar system 4 billion years ago. Unlike its siblings, Callisto shows little evidence of internal geological activity. Yet even here, scientific evidence suggests a subsurface ocean might exist, sustained by leftover heat from the moon's formation and radioactive decay in its interior. As New Horizons swept past Jupiter at its closest approach of 1.4 million miles from the planet's cloud tops, it executed its primary objective perfectly. The gravitational assist bent the spacecraft trajectory by precisely the right amount, setting it on course for Pluto with increased velocity. The encounter had trimmed 3 years off the journey time. The spacecraft also turned its attention to Jupiter's ring system, a faint structure discovered by Voyager 1 in 1979. New Horizons captured images showing how tiny particles in these rings scatter sunlight, helping scientists understand their composition and dynamics. The rings are continuously replenished by meteoroid impacts on small inner moons, which blast particles into orbit around Jupiter. Throughout the encounter, New Horizons instruments worked continuously, gathering data on Jupiter's magnetosphere, the vast region of space dominated by the planet's magnetic field. This magnetosphere is enormous, extending several million miles into space, and particles trapped within it create intense radiation belts far more powerful than Earth's Van Allen belts. The spacecraft measured the composition and energy of these particles, adding to our understanding of how giant planets interact with their space environments. The Jupiter encounter demonstrated that New Horizons systems were functioning beautifully. Every instrument had performed flawlessly, and the spacecraft had executed complex maneuvers with precision. The mission team had also learned valuable lessons about operating the spacecraft that would prove crucial during the Pluto encounter 8 years later. As New Horizons sped away from Jupiter, accelerated to nearly 51,000 miles per hour relative to the Sun, it left behind a treasure trove of images and data. The giant planet gradually shrank in the rear-view cameras, its moons becoming points of light once more. Ahead lay another 8 years of travel through the dark void, but the spacecraft was healthy, swift, and bound for its ultimate destination. The gravity dance with Jupiter had been a perfect success, and the long coast to Pluto could begin. After the excitement of Jupiter, New Horizons entered a phase of profound solitude. Ahead lay more than 8 years of travel through the vast emptiness between the giant planets and the realm of the ice dwarfs. This region of space is almost incomprehensibly empty, a darkness broken only by the distant, steady light of stars and the faint glow of the sun, now appearing as merely the brightest star in the sky rather than the brilliant disk we know from Earth. To conserve its limited resources, New Horizons was placed into hibernation mode for most of this journey. During these sleep periods, which lasted from several weeks to several months, most of the spacecraft systems were powered down. Only essential functions continued. The heater that kept its electronics from freezing, the clock that measured time, and the transmitter that sent occasional status reports back to Earth. These reports took over 4 hours to reach ground controllers at the speed of light, covering billions of miles of space. The spacecraft would wake occasionally for annual checkouts, during which ground controllers would verify that all systems remained healthy and perform routine maintenance. During these periods, which typically lasted several weeks, engineers would test each instrument, calibrate sensors, download stored data, and upload any necessary software updates. New Horizons would test fire its small thrusters to ensure they still function properly, and controllers would precisely measure the spacecraft trajectory to confirm it remained on course for Pluto. While New Horizons slept, the mission team on Earth remained busy. Scientists refined their plans for the Pluto encounter, deciding exactly when and where to point each instrument. They studied images and data from ground-based telescopes and the Hubble Space Telescope, learning everything possible about Pluto before the encounter. What they discovered both excited and worried them. Pluto had at least 5 moons, and no one knew if more might lurk in the system, too small and faint for Earth's telescopes to detect. The discovery of Pluto's moons had occurred gradually. Charon, the largest, was discovered in 1978 by astronomer James Christie, who noticed that images of Pluto appeared slightly elongated at regular intervals. This wasn't a distortion, but rather Charon orbiting Pluto, so close that the two appeared as a single object in most telescopes. Charon is enormous compared to Pluto, more than half Pluto's diameter, making them more like a binary dwarf planet system than a traditional planet and moon. In 2005, using the Hubble Space Telescope, astronomers discovered 2 additional tiny moons, later named Nix and Hydra. They orbit much farther from Pluto than Charon, moving through space like distant sentinels around the binary pair. Then, in 2011 and 2012, as Hubble continued monitoring the system in preparation for New Horizons' arrival, 2 more moons appeared, Kerberos and Styx, even smaller and fainter than Nix and Hydra. This crowded system raised concerns for mission planners. If 5 moons existed, might there be more? More importantly, in a system with so many orbiting bodies, collisions might occasionally occur, creating debris fields that would be invisible to telescopes, but potentially catastrophic for a spacecraft traveling at over 30,000 miles per hour. At that velocity, even a particle the size of a rice grain carries enough energy to severely damage New Horizons. The mission team developed contingency plans, plotting alternate trajectories that would take New Horizons through the system by different paths if hazardous debris were detected. These paths would sacrifice some scientific observations but would keep the spacecraft safer. Meanwhile, telescopes continued searching for any signs of additional moons or rings that might pose a threat. As the years passed and New Horizons sailed onward, its distance from the sun grew ever greater. The intensity of sunlight decreased with the square of the distance. So as the spacecraft moved from Jupiter's orbit to regions beyond, the sun's warmth and light dimmed considerably. Out here, the sun provides only 1/1000th of the light and heat it delivers to Earth. Solar panels would be useless in such dim conditions, which is why New Horizons relied on its nuclear power source. The stars themselves remained constant companions during this long crossing. Unlike planets that shift position against the starry background, the stars maintain their configurations, the same constellations visible from New Horizons as from Earth, though with slightly different perspectives. The spacecraft was traveling fast enough that nearby stars did show minute parallax shifts, the positions changing ever so slightly relative to more distant stars as New Horizons' viewpoint changed across billions of miles. During wake periods, New Horizons occasionally conducted scientific observations, even while far from any major solar system body. Its dust counter continuously monitored the space environment, detecting microscopic particles that pervade interplanetary space. These measurements helped scientists understand the distribution of dust throughout the solar system, material that originates from comets, asteroids, and even interstellar space. The spacecraft also served as a test bed for navigation techniques. Engineers used observations of known stars to practice and refine the optical navigation methods they would use during the Pluto encounter. By imaging distant stars and measuring their positions relative to foreground objects, navigation teams could determine New Horizons' position and trajectory with remarkable precision. Communication with Earth remained a vital link across the growing void. The Deep Space Network, NASA's collection of massive radio antennas in California, Spain, and Australia, maintained contact with New Horizons, sending commands and receiving data. As the distance grew, so did the time delay in communications. By the time New Horizons reached Pluto's distance, commands took over 4.5 hours to reach the spacecraft, and responses took another 4.5 hours to return. This meant that the spacecraft had to be largely autonomous, capable of executing complex sequences without real-time guidance from Earth. The mission team also had to carefully manage New Horizons' limited data storage and transmission capabilities. The spacecraft could store about 8 gigabytes of data in its solid-state recorders, roughly equivalent to a few thousand high-resolution images. However, transmitting this data back to Earth took considerable time. At Pluto's distance, the spacecraft could only transmit data at about 1 to 2 kilobits per second, meaning that downloading a single high-resolution image could take an hour or more. The team would spend more than 15 months after the Pluto encounter downloading all the stored data. Throughout these long years, the spacecraft systems aged gracefully. The electronics were slowly accumulating radiation damage from cosmic rays, high-energy particles that constantly stream through space. Engineers monitored this carefully, knowing that too much radiation damage could cause components to fail. Fortunately, New Horizons have been designed with radiation-hardened components and redundant systems to ensure it could complete its mission despite this gradual degradation. As 2014 arrived, the long crossing was nearing its end. Pluto remained invisible to New Horizons cameras, still too distant to appear as more than a point of light indistinguishable from background stars. But it was there, waiting, and with each passing day, New Horizons drew closer to its destination. On December 6, 2014, New Horizons stirred from its final hibernation. The command to wake had been sent from Earth months earlier, and now, as programmed, the spacecraft reactivated its full suite of systems. Internal heaters warmed scientific instruments to their operating temperatures, computers ran diagnostic checks, and transmitters powered up to send a simple message across the vast distance. I am awake, I am healthy, and I am ready. When that signal reached Earth over 4 hours later, it sparked celebrations at Mission Control in the Johns Hopkins University Applied Physics Laboratory in Maryland. After more than 8 years and nearly 3 billion miles of travel, the most critical phase of the mission was about to begin. The encounter sequence that would dominate the next 7 months had commenced. There would be no more sleeping now. New Horizons would remain fully active, all systems engaged, as it executed the most detailed study ever conducted of a world in the outer solar system. The spacecraft's cameras began their patient work of optical navigation. By photographing Pluto and its moons against the background stars, navigators could determine precisely where the spacecraft was and exactly where it was heading. These measurements needed to be extraordinarily accurate. The mission plan called for New Horizons to pass within approximately 7,700 miles of Pluto's surface at closest approach, threading a needle through space at over 30,000 miles per hour. If the spacecraft arrived at the wrong position by even a few dozen miles, some critical observations might be missed. Throughout January and February of 2015, Pluto gradually grew in New Horizons cameras from a mere point of light into a tiny disk, though still too small to show meaningful detail. By late April, the distance had closed enough that New Horizons images surpassed the best views ever obtained by Hubble Space Telescope. For the first time in history, humanity was seeing features on Pluto's surface that had never been visible before. Blurry patches hinted at regions of different brightness, suggesting varied terrain, but the details remained tantalizingly unclear. The spacecraft conducted a series of trajectory correction maneuvers during this approach phase, firing its small thrusters to refine its path. Each adjustment had to be calculated with extreme precision. The team used increasingly detailed images of Pluto and Charon to determine their exact positions, then computed the tiny velocity changes needed to ensure New Horizons would arrive at exactly the right place at exactly the right time. These maneuvers also had to account for something engineers had never dealt with before: the gravitational influence of Charon on the spacecraft trajectory. Because Charon is so large relative to Pluto, the two bodies orbit a common center of mass located in space between them, creating complex gravitational dynamics. As spring progressed into early summer, excitement built with each new image downlinked from the spacecraft. In May, New Horizons cameras began revealing Pluto's surface features in unprecedented detail. Bright and dark regions appeared, suggesting varied geological compositions. The dwarf planet was revealing itself as far more complex than the simple ball of ice many had imagined. One particularly bright region near Pluto's equator caught attention immediately, though its nature remained mysterious at these distances. The mission team had choreographed every moment of the encounter sequence with meticulous care. Because New Horizons would spend only a few hours in close proximity to Pluto, traveling too fast to orbit, every observation had to be perfectly timed. The spacecraft would gather data continuously from 1 week before closest approach until 1 week after, executing a precisely scripted sequence of camera exposures, spectroscopic measurements, and plasma and dust observations. Once started, this sequence would run autonomously, with New Horizons making its own decisions about when to point each instrument at which target, because the communication delay meant that ground controllers couldn't provide real-time commands. The scientific objectives were ambitious and comprehensive. Scientists wanted to map the geology of Pluto and Charon, determining their surface compositions and looking for evidence of geological activity. They hoped to characterize Pluto's tenuous atmosphere, measuring its composition, temperature, and how it escapes into space. The team wanted to search for additional moons or rings that might exist, and they aimed to study the smaller outer moons Nix, Hydra, Kerberos, and Styx, learning about their shapes, sizes, compositions, and orbital characteristics. Most fundamentally, they wanted to understand Pluto and Charon as members of the Kuiper Belt, the vast region of icy bodies beyond Neptune that represents the solar system's third zone, after the rocky inner planets and the gas and ice giants. Throughout June, as New Horizons closed to within tens of millions of miles, Pluto's features continued sharpening in the images. Scientists could now clearly see the bright equatorial region, informally named the whale due to its shape, positioned next to a large dark area. Distinct bright and dark regions suggested varied terrain types. The team speculated about what might create such diversity: impact craters, volcanic deposits, or perhaps regions of different ices with varying reflectivity. The smaller moons also began revealing their secrets. Observations showed they were rotating chaotically rather than keeping one face toward Pluto as most moons do. This strange behavior likely resulted from their positions in the complex gravitational field created by the Pluto-Charon binary system, where the gravitational tugs from two large bodies in close proximity prevented the moon from settling into simple tidally locked rotations. In early July, just days before closest approach, New Horizons captured an image that would become iconic. As the spacecraft looked back toward Pluto with the sun behind the dwarf planet, it photographed Pluto as a crescent, with the bright whale region now revealed in stunning clarity as a vast, smooth plain. But the detail that captured everyone's attention was a large, bright, heart-shaped feature spanning nearly 1,000 miles across Pluto's surface. This heart, immediately and informally named Tombaugh Regio after Pluto's discoverer, would become the defining feature of Pluto's appearance and one of the most recognizable planetary features in our solar system. The final days before closest approach were filled with anticipation and careful attention to every detail. Engineers monitored the spacecraft's systems constantly, watching temperatures, power levels, and the status of each instrument. Mission Control prepared contingency procedures for every conceivable problem. The team's efforts of nearly a decade would culminate in a single day when New Horizons would execute the most detailed observations of Pluto ever possible, gathering data that would take more than a year to fully transmit back to Earth. As July 14, 2015, dawned, New Horizons was ready. The spacecraft had traveled farther and faster than any previous mission to reach a new world. It carried the dreams of generations of planetary scientists and space enthusiasts. And now, finally, after nearly 10 years of flight, it would make history. At 7:49 a.m. Eastern Daylight Time on July 14, 2015, New Horizons swept past Pluto at a distance of 7,800 miles from its surface, moving at 30,800 miles per hour. At this closest approach, the spacecraft was too busy collecting data to communicate with Earth. Its antenna was pointed away from our planet, aimed instead at Pluto and its moons, gathering every possible observation. Back on Earth, mission scientists and space enthusiasts around the world waited anxiously for the scheduled signal that would confirm New Horizons had survived its high-speed passage through the Pluto system. The flyby was designed to happen during relative silence. For 13 hours spanning closest approach, New Horizons would focus entirely on science, its instruments continuously recording data about Pluto, Charon, and the smaller moons. The spacecraft's computers stored this information in its solid-state memory, a precious cargo of discovery that would be transmitted home over the following months. Only after the encounter sequence completed would New Horizons reorient its antenna toward Earth and send the awaited message. I am healthy, and I have the data. That confirmation signal arrived at 8:53 p.m. that evening, traveling for 4 hours and 25 minutes across the 3 billion miles from Pluto to Earth at the speed of light. When the tones indicating a successful encounter were detected by the Deep Space Network antennas, Mission Control erupted in celebration. The spacecraft had survived. The decades of planning, years of building, and 9.5 years of flight had led to this moment of triumph. New Horizons had visited Pluto, and our understanding of the outer solar system would never be the same. But the true revelations emerged in the days and weeks that followed, as New Horizons began transmitting its stored images and data back to Earth. The first high-resolution images of Pluto's surface stunned scientists and public alike. The dwarf planet was nothing like what anyone had expected. Instead of the ancient, heavily cratered surface typical of small, geologically dead worlds, Pluto displayed remarkable diversity and clear evidence of recent geological activity. The heart-shaped feature, Tombaugh Regio, dominated Pluto's encounter hemisphere. Its western lobe, a vast plain informally named Sputnik Planitia, appeared almost impossibly smooth, completely lacking impact craters. On planetary surfaces, the absence of craters tells scientists something profound. The terrain is young, recently resurfaced by geological processes. On Pluto, a world 3 billion miles from the Sun where surface temperatures hover around minus 375 degrees Fahrenheit, such recent activity was completely unexpected. Sputnik Planitia proved to be a vast sheet of nitrogen ice, approximately the size of Texas and Oklahoma combined. Its surface was divided into strange polygonal cells, each about 10 to 20 miles across, separated by shallow troughs. These cells appear to be the surface expression of convection in the ice layer, where warmer nitrogen ice from below rises slowly to the surface, spreads outward, and then sinks at the cell boundaries as it cools, creating a pattern similar to convection cells in boiling water, though operating at an incomprehensibly slower pace across millions of years. Along the margins of Sputnik Planitia, the nitrogen ice appeared to be flowing like a glacier, filling craters and valleys in the surrounding terrain. Some regions showed what appeared to be ancient valleys carved into water-ice bedrock, now filled with glacial nitrogen. These flows demonstrated that despite the extreme cold, ices on Pluto can deform and flow over geological time, shaped by the dwarf planet's weak gravity. The eastern portion of the heart, separated from Sputnik Planitia by a mountain range, showed a completely different character. This region, informally called Cthulhu Regio, appeared much darker, covered in reddish-brown material. The colors suggest complex organic compounds called tholins, which form when methane in Pluto's atmosphere is broken apart by ultraviolet sunlight and cosmic rays, creating complex hydrocarbons that drift down to coat the surface. This region was also ancient, densely cratered, telling of billions of years of meteoroid bombardment. Perhaps most surprising were Pluto's mountains. Along the edges of Sputnik Planitia and elsewhere on Pluto's surface, New Horizons discovered mountain ranges rising up to 2 and even 3 miles high. These peaks, comparable in height to the Rocky Mountains on Earth, couldn't be made of nitrogen or methane ice, which are far too soft to support such structures on a world with Pluto's gravity. Instead, the mountains must be composed of water ice, which at Pluto's temperatures is as strong and rigid as rock. The discovery of these mountains immediately raised questions about how they formed and what kept Pluto geologically active enough to create them. Across Pluto's surface, New Horizons discovered an astonishing variety of terrain types, each telling part of the story of this complex world. There were regions with patterns that looked like snakeskin, others with sharp ridges aligned in parallel, and areas covered with what appear to be dune-like features, though how dunes could form in Pluto's thin atmosphere remained puzzling. In some locations, the spacecraft found what appeared to be vast fields of pits, possibly formed by the sublimation of nitrogen ice, turning directly from solid to gas without melting. Pluto's atmosphere, though incredibly tenuous with a surface pressure only about 100,000th of Earth's, proved surprisingly extensive and complex. As New Horizons looked back at Pluto after closest approach, with the sun behind the dwarf planet, the spacecraft's instruments observed sunlight filtering through atmospheric layers. These observations revealed hazes extending up to 130 miles above Pluto's surface, multiple times higher than expected. The haze layers appeared remarkably distinct, like a stack of pancakes in the sky. The composition of Pluto's atmosphere matched expectations, mostly nitrogen, with traces of methane and carbon monoxide. But the structure and behavior of the atmosphere held surprises. The gases are constantly escaping into space, a process called atmospheric loss. Solar radiation heats the thin atmosphere enough that gas molecules reach escape velocity and stream away from Pluto. New Horizons measured this escape rate, finding that Pluto loses hundreds of tons of nitrogen every hour, though this is negligible compared to the vast quantities of nitrogen ice on the surface. The colors visible in Pluto's atmosphere and on its surface reveal the active photochemistry occurring constantly. Ultraviolet light from the distant sun breaks apart methane molecules in the upper atmosphere. These fragments recombine into more complex hydrocarbons, which aggregate into tiny haze particles. These particles drift down through the atmosphere, eventually settling on the surface as the reddish-brown tholins that coat much of Pluto. This process links Pluto's atmosphere directly to its surface geology in a cycle of chemistry that has operated for billions of years. The discoveries from Pluto's Flyby rewrote textbooks and challenged long-held assumptions about small, cold worlds in the outer solar system. Here was a dwarf planet showing clear evidence of recent geological activity despite being so distant from the sun that its surface receives only 1,000th the sunlight that Earth receives. The heat driving Pluto's geological activity couldn't come from the sun. Instead, it likely comes from radioactive decay in Pluto's rocky core and possibly from the freezing of a subsurface ocean, which would release tremendous amounts of heat over geological time. New Horizons revealed Pluto not as a simple, frozen, dead world, but as a geologically complex, active planet with diverse terrains, a dynamic atmosphere, and recent surface changes. The heart-shaped Tombaugh Regio became an icon, but it was just one feature on a world full of mysteries waiting to be understood through years of analysis of the data New Horizons collected during those critical hours in July 2015. While Pluto captured most of the public's attention and imagination, New Horizons also conducted detailed studies of Pluto's largest companion, Charon, and the system's 4 much smaller outer moons. Each of these bodies proved fascinating in its own right, adding depth and complexity to our understanding of this distant system and its violent origin. Charon, discovered in 1978, orbits Pluto at a distance of just 12,200 miles, completing one orbit every 6.4 Earth days. This is the same period as Pluto's rotation, meaning Pluto and Charon are tidally locked to each other, always showing the same faces to one another like cosmic dance partners frozen in an eternal embrace. At 750 miles in diameter, Charon is roughly half the size of Pluto itself, making this the most evenly sized binary system of any planet or dwarf planet in our solar system. They orbit a common center of mass located in space between them, making them more like a double dwarf planet than a traditional planet-moon system. The size and proximity of Charon create fascinating dynamics. From Pluto's surface, Charon would appear enormous in the sky, roughly 7 times larger than our moon appears from Earth, hanging always in the same position in the sky and never rising or setting. An observer on Pluto's near side would always see Charon, while someone on Pluto's far side would never see it at all. Similarly, an observer on Charon would see Pluto fixed in position, unchanging in the sky. When New Horizons images of Charon arrived on Earth, scientists immediately noticed something remarkable. Charon looked completely different from Pluto. While Pluto's surface was dominated by nitrogen, methane, and carbon monoxide ices, Charon's surface appeared to be primarily water ice, which at these temperatures behaves like bedrock. The moon's north polar region was covered with a distinctive reddish-brown material, creating a stark color contrast informally nicknamed Mordor Macula after the Dark Land in J.R.R. Tolkien's fiction. This dark polar material likely consists of tholins, similar to those found on Pluto, but with an interesting origin story. Scientists theorize that methane escaping from Pluto's atmosphere and the small amounts present on Charon are captured by the moon's weak gravity, particularly in the cold trap of the polar region during its long winter when temperatures drop even lower than usual. There, solar radiation and cosmic rays process the methane into complex organic compounds that accumulate over millions of years, creating the dark cap. Charon's surface displayed another surprise, a landscape marked by extensive tectonic features. The moon's surface is cut by enormous chasms and cliffs, some stretching for hundreds of miles and dropping 4 miles or more in depth. These features appear to be fractures created as Charon's interior froze and expanded. If Charon once had a subsurface ocean beneath its icy crust, as scientists suspect, the gradual freezing of that ocean would have caused the ice to expand, cracking the surface and creating the dramatic fault lines visible today. One of Charon's most prominent features is an enormous cliff system informally called Serenity Chasma, a canyon that appears to be part of a vast system of fractures extending at least 1,000 miles across Charon's surface. These cliffs and canyons are among the longest and deepest in the solar system, testimony to powerful geological forces that shaped Charon's surface in its past. Unlike Pluto, much of Charon's surface is heavily cratered, indicating ancient terrain that has remained largely unchanged for billions of years. But certain regions, particularly in the southern hemisphere, appear much smoother and less cratered, suggesting geological resurfacing in the relatively recent past. The nature of this resurfacing remains somewhat mysterious. Some scientists propose that cryovolcanism, the eruption of icy materials from the interior, might have resurfaced these regions, though direct evidence for volcanic features is limited. The smaller moons of the Pluto system offered their own surprises. Nix, Hydra, Kerberos, and Styx orbit much farther from Pluto than Charon, ranging from 30,000 to 65,000 miles away. These tiny moons are irregular in shape, resembling lumpy potatoes more than spheres. Nix measures roughly 30 miles in its longest dimension, Hydra about 40 miles, while Kerberos and Styx are smaller still, just 8 to 12 miles across. New Horizons discovered that these small moons are surprisingly bright, reflecting significantly more sunlight than expected. Their surfaces appear to be covered in relatively clean water ice, giving them high albedos, the scientific term for reflectivity. This brightness suggests that their surfaces are either young or continuously refreshed by some process, perhaps by micrometeoroid impacts that excavate fresh ice from beneath dust layers, or by sublimation processes that remove darker materials. Most surprisingly, observations revealed that these small moons are not tidally locked like most moons in the solar system. Instead, they tumble chaotically through space, their rotation rates and axes constantly changing. This chaotic rotation likely results from their positions in the complex gravitational field created by Pluto and Charon. The gravitational pulls from both bodies, combined with their orbital motions, create torques that prevent the moons from settling into stable rotation states. The very existence and characteristics of all these moons strongly suggest a violent origin for the Pluto system. The leading theory proposes that billions of years ago, Pluto collided with another large Kuiper Belt object. This impact was energetic enough to blast material into orbit around Pluto, and this debris gradually coalesced to form Charon and the smaller moons. This is similar to the giant impact hypothesis for Earth's moon's formation, though the Pluto collision appears to have been more extreme relative to the sizes of the bodies involved. Computer simulations of such a collision can reproduce the Pluto-Charon system's characteristics. The mass ratio between Pluto and Charon, their spacing, and even the presence of the small outer moons. The impact would have been catastrophic, melting large portions of both bodies and creating a disk of debris. Charon would have formed relatively quickly from this debris, while the outer moons likely coalesced more slowly from material in the outer portions of the disk. This violent history helps explain some of Pluto and Charon's geological features. The heat generated by such a massive impact would have been enormous, potentially enough to melt interiors and create subsurface oceans. The subsequent slow freezing and cooling over billions of years would drive the geological activity visible today. The impact might even help explain the peculiar location of Sputnik Planitia on Pluto, as some models suggest the basin formed from the giant impact or from a subsequent large impact on the already formed Pluto. New Horizons' study of Charon and the small moons thus provided crucial context for understanding Pluto itself. These bodies are not separate from Pluto's story, but integral parts of it, all born from the same violent event and shaped by billions of years of evolution in the cold depths of the outer solar system. Together, they form a system that continues to surprise and enlighten scientists, revealing the dynamic nature of even the coldest, most distant worlds. As New Horizons sped away from Pluto in the hours and days after closest approach, it continued observing the dwarf planet system, its cameras now looking back at Pluto's night side and far side, regions that have been invisible during the approach. These departing observations provided different perspectives and completed the mission's survey of the system, while the increasing distance allowed the spacecraft to capture context images showing Pluto and its moons together. One of the most memorable images captured during departure showed Pluto as a crescent, backlit by the sun, with layers of haze in its atmosphere glowing in the sunlight like a delicate blue halo around the dwarf planet. This image revealed the vertical structure of Pluto's atmosphere in exquisite detail, showing distinct layers stacked up to 80 miles above the surface. The beautiful blue color came from tiny haze particles scattering sunlight, the same phenomenon that makes Earth's sky blue, though the composition and altitude of these hazes were unique to Pluto. The spacecraft also looked back at Charon during departure, capturing the moon's night side faintly illuminated by sunlight reflected off Pluto, a phenomenon similar to Earthshine on our own moon. These observations helped scientists understand the reflective properties of both bodies and provided additional data about their surface compositions and structures. Throughout the weeks following the encounter, New Horizons began the long process of transmitting its stored data back to Earth. The spacecraft had collected approximately 6.25 gigabytes of data during the encounter, including thousands of images and millions of measurements from its various instruments. At the data transmission rate possible at Pluto's distance, around 1 to 2 kilobits per second, downloading this treasure trove would take more than 15 months, continuing until October 2016. The slow data return was governed by the physics of radio communication across such vast distances. New Horizons transmitted using its radio dish antenna, broadcasting at several watts of power, similar to a bright LED light bulb. By the time these signals reached Earth, having spread out across billions of miles, they were unimaginably faint, requiring the largest antennas of NASA's Deep Space Network to detect them. Each bit of data had to be carefully error-corrected to ensure accuracy, as the weak signals were susceptible to interference and noise. Mission planners had prioritized the data carefully. The most important images and measurements were transmitted first in case any problem prevented the full data return. Scientists received select high-priority images within days of the encounter, allowing them to begin analysis and share results with the public. But the complete, highest-resolution images and the full datasets from all instruments arrived over many months, with new discoveries continuing long after the encounter itself. As New Horizons transmitted its data and departed the Pluto system, mission planners turned their attention to an important question: what would the spacecraft do next? New Horizons remained healthy and fully functional, with enough fuel and power to continue operating for decades. The spacecraft's nuclear power source would continue generating electricity until at least the 2030s, declining slowly as the plutonium decayed, but remaining adequate for operations. The extended mission plan called for New Horizons to visit another object in the Kuiper Belt, the vast region of icy bodies beyond Neptune's orbit. This region contains thousands of objects, remnants from the solar system's formation 4.6 billion years ago. These pristine, frozen worlds preserve conditions from the solar system's birth, and studying them helps scientists understand how planets formed and what the early solar system was like. Finding a suitable target presented challenges. The object needed to be reachable with New Horizons remaining fuel for trajectory corrections, and it needed to be along or near the spacecraft's current trajectory, as New Horizons didn't carry enough fuel for major course changes. It also needed to be small enough to study meaningfully during a flyby, but large enough to be scientifically interesting. Beginning in 2014, even before the Pluto encounter, mission scientists began using powerful ground-based telescopes and the Hubble Space Telescope to search for potential targets. The search focused on a narrow region of sky along New Horizons' trajectory, looking for faint objects that the spacecraft could reach. This was extraordinarily challenging, as Kuiper Belt objects are small and dark, reflecting little sunlight, making them difficult to detect even with the best telescopes. The search campaigns observed the same regions of sky repeatedly over several months. By comparing images taken at different times, astronomers could identify objects that had moved relative to background stars, indicating they were relatively nearby members of the Kuiper Belt rather than distant stars or galaxies. Several potential targets were identified and their orbits calculated to determine which could be reached by New Horizons. In August 2015, just weeks after the Pluto flyby, mission scientists announced they had selected a target for New Horizons' extended mission. The object, initially designated 2014 MU-69 and later officially named Arrokoth, was a small Kuiper Belt object discovered in June 2014 specifically during the target search. It measured roughly 20 miles across, tiny compared to Pluto, and orbited the Sun about 1 billion miles beyond Pluto's orbit. Reaching Arrokoth would require New Horizons to adjust its trajectory through a series of maneuvers in 2015 and 2016. These trajectory correction maneuvers would change the spacecraft velocity by just a few meters per second. But this small change, applied billions of miles from the target, would bend New Horizons' path enough to intercept Arrokoth in January 2019. The extended mission to Arrokoth was approved by NASA in 2016, ensuring that New Horizons would continue its exploration of the outer solar system. But this mission lay years in the future. For now, as 2015 drew to a close, New Horizons continued transmitting its Pluto data while coasting through the outer solar system, having accomplished the primary mission that had motivated its creation. The spacecraft had visited Pluto, revealed its wonders, and was now prepared to venture even deeper into the Kuiper Belt. Behind New Horizons, Pluto receded into the distance, appearing once again as just a bright point of light, indistinguishable from a star to the spacecraft's cameras. But it was no longer unknown. New Horizons had illuminated this distant world, revealing a complex, active, geologically diverse dwarf planet that challenged and expanded our understanding of what planetary bodies can be. The heart-shaped Tombaugh Regio would endure as a symbol of the mission and of humanity's drive to explore the unknown reaches of our cosmic neighborhood. After the triumph at Pluto, New Horizons embarked on an extended journey deeper into the Kuiper Belt toward its next target, the small object initially known as 2014 MU-69 and later officially named Arrokoth, a Native American term meaning sky in the Powhatan language. This encounter would mark the farthest exploration of any object by a spacecraft, taking place 4 billion miles from the Sun, 1 billion miles beyond Pluto's orbit. The trajectory correction maneuvers executed in late 2015 successfully placed New Horizons on a course for Arrokoth, and the spacecraft settled into another period of relative dormancy as it crossed the vast distances. The years between Pluto and Arrokoth were spent transmitting the last of the Pluto data, conducting engineering tests, and preparing for the next encounter. The spacecraft also continued its observations of the Kuiper Belt environment, measuring dust particle distributions and the properties of the solar wind at these extreme distances. Arrokoth represented a scientific target fundamentally different from Pluto. While Pluto is large enough that its own gravity has shaped it into a sphere and geological processes have altered its surface, Arrokoth is much smaller, barely 20 miles in longest dimension, and has remained essentially unchanged since it formed during the solar system's birth approximately 4.6 billion years ago. Scientists hoped that studying Arrokoth would provide insights into the processes that built planets from smaller bodies. As New Horizons approached Arrokoth through 2018, the object appeared in the spacecraft's cameras first as an indistinct point of light, slowly growing and resolving. The first images that showed any detail revealed something unexpected. Arrokoth appeared elongated, suggesting either a highly elliptical shape or possibly two objects close together. As resolution improved, the truth became clear. Arrokoth consisted of two lobes in contact with each other, a shape often described as resembling a snowman or, more technically, a contact binary. The flyby occurred on January 1st, 2019 at 12:33 a.m. Eastern Standard Time, with New Horizons passing just 2,200 miles from Arrokoth's surface. This was much closer than the Pluto encounter, and because Arrokoth is so much smaller and darker than Pluto, the close approach was necessary to gather sufficient data. The encounter was perfectly executed, with New Horizons instruments collecting detailed images and measurements during the brief hours when Arrokoth filled the spacecraft's view. The images returned in the days and weeks following the encounter revealed Arrokoth's structure in remarkable detail. The object consists of two lobes that touch gently at a narrow neck. The larger lobe, measuring roughly 13 miles across, connect to the smaller lobe, about 9 miles in diameter. Both lobes are relatively flat, like pancakes pressed together, rather than spherical. This unusual shape provided immediate clues about Arrokoth's formation. Arrokoth's surface appeared remarkably smooth and lacking in major geological features. There were no obvious impact craters, despite the object's presumed age of 4.6 billion years. The surface color was uniformly reddish-brown, consistent with the presence of complex organic compounds called tholins, created by the irradiation of simpler carbon-bearing molecules by sunlight and cosmic rays over billions of years. Small pits and brighter patches dotted the surface, likely indicating subtle variations in composition, but overall Arrokoth appeared geologically inactive and pristine. The shape and gentle connection between the two lobes told a story about Arrokoth's formation that challenged previous theories about how planetesimals, the building blocks of planets, came together in the early solar system. Earlier models suggested that planetesimals formed through collisions, with smaller objects smashing together at relatively high speeds and sticking together. But Arrokoth's shape indicates a much gentler origin. The two lobes appear to have come together at low speed, perhaps just a few miles per hour, more like a kiss than a collision. They touched and remained in contact, their mutual gravity holding them together without deforming or disrupting either lobe. This gentle merger preserves the original shapes of both lobes, which themselves are flattened, suggesting they formed through the gradual accumulation of even smaller particles that settled into rotating, flattened clouds before coalescing. This discovery supported a newer model of planetesimal formation called streaming instability, in which concentrations of dust and ice in the early solar system's protoplanetary disk become gravitationally unstable and collapse directly into objects roughly the size of Arrokoth's lobes. These objects, once formed, then encounter each other at low relative velocities and merge gently, building larger bodies. This process differs significantly from hierarchical collisional accumulation and may explain how planets could form quickly enough to match constraint from observations of other planetary systems. Arrokoth's very existence in its current pristine state tells us something important about the Kuiper Belt. The object has remained virtually unchanged for 4.6 billion years, orbiting the Sun in the cold, dark outer solar system. It has never been heated significantly by the Sun, never approached the inner solar system where warmer temperatures might have altered it, and has avoided violent collisions that would have disrupted or reshaped it. It represents a frozen sample of the solar system's birth material, preserved across the eons. The encounter with Arrokoth also provided data about the object's composition and internal structure. Spectroscopic observations revealed signatures of water ice, methanol, and complex organic molecules on its surface. The presence of methanol was particularly intriguing, as this simple alcohol is thought to have been common in the early solar system, but is easily lost if an object is heated. Its presence on Arrokoth confirmed that the object has never been significantly warmed. Arrokoth's density, calculated from observations of how the object's weak gravity affected New Horizons' trajectory, indicated that it is not very compact. The object appears to have a significant amount of empty space in its interior, suggesting a loose, porous structure rather than solid ice throughout. This porosity is consistent with gentle formation, where particles stuck together without being compressed by high-speed impacts. The New Horizons team also searched for moons or rings around Arrokoth, but found none. The object's gravity is far too weak to hold onto an atmosphere, and any material blasted off its surface by micrometeorite impacts would escape into space rather than form a ring. This isolation makes Arrokoth simpler to study and understand than more complex systems like Pluto with its multiple moons. The Arrokoth encounter marked the culmination of New Horizons' formal mission objectives, but it also opened new questions about the formation of planetary systems. Every detail observed, from the smooth connection between the lobes to the uniform surface color and the flattened shapes, provided constraints for models of planet formation. Scientists would spend years analyzing the data, comparing Arrokoth to other small solar system bodies, and refining theories about how the planets, including Earth, came to be. As New Horizons departed Arrokoth and the object shrank back to a point of light in the spacecraft's rear-view cameras, another chapter in the mission's remarkable journey concluded. The spacecraft had now visited two completely different types of objects in the outer solar system. Pluto, a large, geologically active dwarf planet with complex interactions between its surface, atmosphere, and moons, and Arrokoth, a small, pristine, unchanged relic from the solar system's formation. Together, these encounters transformed our understanding of the Kuiper Belt and the distant frontier of our planetary system. As New Horizons continues its journey outward from the Sun, traveling at over 30,000 miles per hour, it moves ever deeper into the Kuiper Belt, the vast region of space beyond Neptune's orbit filled with thousands of icy bodies. This region, discovered in the early 1990s after being predicted decades earlier by astronomer Gerard Kuiper, represents a frontier of our solar system that we are only beginning to understand. New Horizons, as it explores this region, serves as humanity's first dedicated explorer of this distant realm. The Kuiper Belt extends from roughly Neptune's orbit at about 30 astronomical units from the Sun, or 30 times Earth's distance from the Sun, to perhaps 50 astronomical units or beyond. An astronomical unit, abbreviated AU, is the average distance from Earth to the Sun, about 93 million miles, and provides a convenient unit for measuring distances in the solar system. At 30 Australian dollars, sunlight is 900 times dimmer than at Earth, and temperatures plunge to around minus 390 degrees Fahrenheit. This region contains countless objects, ranging from small bodies just a few miles across to dwarf planets like Pluto, Eris, Makemake, and Haumea. These objects are remnants from the solar system's formation, material that never accumulated into a full-size planet. In the solar system's early days, this region was likely much more densely populated, but gravitational interactions with Neptune scattered many objects outward into more distant orbits or ejected them from the solar system entirely, leaving the current, more sparsely populated belt. The Kuiper Belt objects fall into different dynamical classes based on their orbits. Classical Kuiper Belt objects, like Arrokoth, orbit in nearly circular paths beyond Neptune and have been relatively undisturbed since formation. Resonant objects, including Pluto, are locked in orbital resonances with Neptune, meaning their orbital periods are simple fractions of Neptune's period. Scattered disk objects have highly elliptical orbits that take them far beyond the main Kuiper Belt, and these objects likely achieve their current orbits through gravitational encounters with Neptune. As New Horizons travels through this region, it continues to make scientific observations even without a close encounter with another object. Its dust counter instrument measures the density of dust particles in interplanetary space at these extreme distances. These measurements help scientists understand how dust is distributed throughout the solar system and how the space environment changes with distance from the Sun. The spacecraft also measures the properties of the solar wind, the stream of charged particles flowing outward from the Sun, studying how it weakens and changes character at these distances. One of New Horizons' continuing observations involves ultraviolet measurements of the background light in space. The spacecraft's ultraviolet instrument can detect a faint glow called the cosmic optical background, which is the combined light from all the galaxies in the universe. Close to the Sun, this background is difficult to measure because sunlight scattered by interplanetary dust overwhelms it. But in the outer solar system, where dust is less dense, New Horizons can make more precise measurements of this fundamental cosmic glow, helping to constrain models of the universe's history and the total number of galaxies. The spacecraft also serves as a platform for parallax measurements of nearby stars. Because New Horizons is so far from Earth, it views nearby stars from a significantly different perspective. By comparing images taken by New Horizons with images taken by telescopes on Earth on the same day, astronomers can precisely measure the apparent shift in star positions, a parallax effect. These measurements help determine accurate distances to nearby stars, refining our understanding of the local stellar neighborhood. Beyond its scientific observations, New Horizons also serves as an ambassador for humanity in the outer solar system. Like the Pioneer and Voyager spacecraft before it, New Horizons carries tokens of Earth culture. The spacecraft includes a small canister containing some of Clyde Tombaugh's ashes, symbolically bringing Pluto's discoverer to the world he found. It also carries a collection of mementos, including state quarters, a piece of Spaceship One, and a CD-ROM containing the names of over 400,000 people who signed up to send their names to Pluto. As New Horizons continues outward, it will eventually cross into a different region of space beyond the Kuiper Belt. The heliopause, the boundary where the solar wind from the sun meets the interstellar medium, lies somewhere between 120 and 150 Australian dollars from the sun, about 4 to 5 times farther than New Horizons' current distance. The Voyager 1 spacecraft crossed this boundary in 2012 at about 122 Australian dollars, and Voyager 2 followed in 2018 at about 119 Australian dollars. New Horizons, if it continues operating, could reach the heliopause sometime in the 2040s or 2050s. Crossing the heliopause would mark New Horizons' entry into interstellar space, though this term is somewhat misleading. The spacecraft would still be gravitationally bound to the sun and would remain part of the solar system for tens of thousands of years as it coasts through the Oort cloud, a theoretical sphere of icy objects surrounding the sun at distances from thousands to hundreds of thousands of AU. But it would be beyond the direct influence of the solar wind, entering the space between stars where different physical processes dominate. The mission team continues to consider possible future observations for New Horizons. While another close encounter with a Kuiper Belt object is unlikely due to the vast distances between objects and the limited fuel remaining for trajectory changes, distant observations of other Kuiper Belt objects are possible. The spacecraft could potentially image dozens of these objects from distances of tens of millions of miles, adding to the catalog of known objects and providing information about their sizes, shapes, colors, and surface properties. New Horizons may also study interstellar dust, particles that originate from outside the solar system and drift through interstellar space. As the spacecraft moves farther from the sun, the ratio of interstellar dust to solar system dust increases, and New Horizons' dust detector can identify and characterize these visitors from other stellar systems. Understanding interstellar dust helps scientists learn about the composition of the interstellar medium and the life cycle of material in the galaxy. The spacecraft's power supply will eventually limit its operations. The plutonium-238 in its radioisotope thermoelectric generator has a half-life of 87.7 years, meaning that its power output decreases by about 1% per year. By the late 2020s, power will become tight enough that some instruments will need to be turned off permanently to keep the spacecraft alive. By the mid-2030s, New Horizons will likely lack sufficient power to operate any science instruments, though it might maintain basic functionality for a few more years. When the power finally becomes insufficient to maintain operations, likely sometime in the 2030s or early 2040s, New Horizons will fall silent. It will continue coasting through space, an inert but enduring monument to human exploration, carrying its recordings of Earth and its tale of journeying to Pluto and Arrokoth. In the unimaginably distant future, hundreds of thousands of years from now, New Horizons might drift close enough to another star system to enter its gravitational influence, though the likelihood of actually colliding with anything is vanishingly small in the vast emptiness of interstellar space. For now, New Horizons remains active and healthy, continuing its solitary journey through the Kuiper Belt, transmitting data and responding to command from the deep space network stations on Earth. Each day carries it roughly 730,000 miles farther from the Sun, adding to the 3 billion miles already traversed. The spacecraft that was built to visit Pluto has become an explorer of the outer solar system's frontier, revealing mysteries and expanding the boundaries of human knowledge with every mile traveled through the cosmic darkness. The New Horizons mission stands as one of the defining achievements of early 21st century space exploration, a testament to human ingenuity, persistence, and curiosity. From its launch in 2006 to its encounters with Pluto and Arrokoth, and its ongoing journey through the Kuiper Belt, the mission has transformed our understanding of the outer solar system and revealed worlds of unexpected complexity and beauty in the cold, dark reaches far from the Sun. The impact of New Horizons extends far beyond the scientific papers published and data archived. The mission captured public imagination in ways that few space missions have, making Pluto a world that had been merely a fuzzy dot in even the best telescopes, into a place with landscapes, weather, geology, and a distinctive personality. The image of Pluto's heart-shaped Tombaugh Regio became iconic, appearing on everything from news broadcasts to children's books, symbolizing both the dwarf planet itself and humanity's capacity to explore the unknown. For planetary science, New Horizons discoveries challenged fundamental assumptions about small, cold worlds. Before the mission, many scientists expected Pluto to be a geologically dead, heavily cratered relic similar to rocky, airless moons in the inner solar system. Instead, New Horizons revealed a world with active geology, a complex atmosphere, diverse terrain types, and evidence of recent surface changes. These discoveries force scientists to reconsider the energy sources that can drive geological activity and the diversity possible among planetary bodies. The smooth plains of Sputnik Planitia, in particular, raise profound questions. The complete absence of craters indicates the surface is less than 10 million years old, incredibly young in geological terms. Yet Pluto is 4.6 billion years old and lies 3 billion miles from the Sun. What heat source could drive such recent activity? The answers likely involve a combination of factors. Heat from radioactive decay in Pluto's rocky core, possible heat from the slow freezing of a subsurface ocean, and the peculiar properties of nitrogen ice at Pluto's temperatures, which can flow and convect even with minimal heating. These insights about Pluto have implications beyond the dwarf planet itself. They suggest that many objects in the outer solar system might be geologically active or have been active in the recent past. This expanded view of where geological activity is possible has influenced how scientists think about dozens of other icy worlds, from Neptune's moon Triton, which may be a captured Kuiper Belt object similar to Pluto, to the icy moons of Jupiter and Saturn, and to other dwarf planets in the Kuiper Belt that remain unexplored by spacecraft. The Arrokoth encounter provided complementary insights, revealing not an active world, but a pristine, unchanged sample of the early solar system. The gentle merger that created Arrokoth's bilobed shape supports models of planet formation that emphasize gentle accumulation over violent collisions, at least to the outer solar system, where relative velocities between objects are low. This has implications for understanding how Earth and the other planets formed from similar building blocks billions of years ago. New Horizons also demonstrated technologies and mission concepts that will influence future exploration. The spacecraft's efficient design, using a radioisotope thermoelectric generator for power and carrying miniaturized instruments, showed how capable probes could be built within reasonable budget constraints. The mission's use of Jupiter for gravity assist, its long hibernation periods during cruise, and its carefully choreographed autonomous encounter sequence all provided lessons for future missions to the outer solar system. Several missions inspired by New Horizons' success are in various stages of planning or development. The Dragonfly mission, scheduled to launch in 2027, will send a rotorcraft to Saturn's moon Titan, exploring that world's methane lakes and organic chemistry. Concepts for missions to Neptune and its moon Triton, to Uranus, and to other Kuiper Belt objects have been proposed, building on the engineering approaches pioneered by New Horizons. A mission to interstellar space, potentially launching in the 2030s, would carry instruments designed to study the heliosphere boundary and the local interstellar medium, completing the exploration of our solar system's extent. The educational impact of New Horizons has been substantial. The mission engaged millions of people worldwide through social media, public talks, documentaries, and news coverage, especially during the Pluto encounter. Students in schools followed the mission's progress, learning about planetary science, engineering, and the process of scientific discovery. Many young people inspired by New Horizons have pursued careers in science and engineering, continuing the cycle of exploration and discovery. The data from New Horizons will continue yielding discoveries for decades. Scientists are still analyzing measurements taken during the Pluto encounter, finding subtle details and patterns that require careful study. The complete understanding of Pluto's atmosphere, the origin of its varied terrain types, the history of its geological activity, and its relationship to other Kuiper Belt objects will emerge gradually as researchers combine New Horizons data with laboratory experiments, computer simulations, and observations from telescopes. Looking to the more distant future, New Horizons represents one of humanity's first steps beyond the planets that have defined our solar system throughout history. The spacecraft carries human presence to the Kuiper Belt and eventually to interstellar space, even as it falls silent in the coming decades. Like the Voyager spacecraft before it and the future probes that will follow, New Horizons extends humanity's reach beyond our home world, exploring territories that our ancestors could not have imagined. The mission also serves as a reminder of the value of patience and long-term commitment in exploration. From the first proposals to study Pluto by spacecraft in the 1990s, through the mission's approval and construction, the 9-year flight to Pluto, and the years of data return and analysis, New Horizons represents decades of dedication by thousands of people. Mission scientists who were young researchers at the project's start became senior figures in their fields by the time of the Pluto encounter. Engineers who built the spacecraft retired before all the data was analyzed. This multi-decade timescale is typical of deep space exploration and requires sustained commitment and continuity. As New Horizons continues its journey outward, now billions of miles from Earth and still receding at thousands of miles per hour, it carries with it the hopes and dreams that motivated its creation. The spacecraft embodies humanity's desire to explore, to understand our place in the cosmos, to push beyond the familiar into the unknown. It demonstrates that even at our small scale in the vastness of space, we can reach across billions of miles to visit and study worlds that our eyes alone can never see clearly. The journey of New Horizons from Pluto's heart to the deep beyond continues. The spacecraft may operate for another decade or two before its power finally wanes. During that time, it will continue observing the Kuiper Belt environment, measuring the space between worlds and slowly approaching the boundary where the sun's influence yields to interstellar space. And beyond that boundary, New Horizons will coast silently onward, an ambassador from Earth journeying among the stars. In the darkness of space, New Horizons travels alone, but carries with it the collective knowledge and aspirations of humanity. It reminds us that we are explorers by nature, driven to investigate even the most distant and challenging frontiers. The mission stands as proof that we can conceive audacious goals, build the tools to achieve them, and actually reach the far edges of our solar system to uncover mysteries billions of miles from home. As we look to the future of space exploration, with missions planned to distant moons, asteroids, and perhaps eventually other stellar systems, New Horizons serves as both inspiration and foundation. It showed what is possible when we commit to exploration, when we build carefully and plan thoroughly, and when we maintain the patience necessary for journeys measured in years and billions of miles. The story of New Horizons is ultimately a story about us, about humanity's place in the universe and our relationship with the cosmos. We are creatures who evolve on a small world orbiting an ordinary star. Yet we possess the curiosity and capability to build machines that can visit the farthest reaches of our solar system and send back images of worlds that no human eyes will likely ever see directly. We can decode the light from those distant worlds to understand their compositions, their histories, and their natures. We can, through science and engineering, extend our senses and presence across billions of miles. And so, as New Horizons sails onward through the eternal night of the outer solar system, it carries forward the best of what we can be: curious, persistent, creative, and forever reaching toward the unknown. The spacecraft's journey from Pluto's heart to the deep beyond is not just a story of a machine traveling through space. It is a story of human exploration, of our quest to understand the universe we inhabit, and of our refusal to accept boundaries to our knowledge and reach. That journey continues, mile by mile, day by day, into the cosmic vastness that beckons us forward.